In this video, we will discuss the operation of a transistor as a switch. Bipolar junction transistors, or BJT in short, is a three-terminal device with 3 layers and 2 p-n junctions. There are two types of BJTs, NPN and PNP. In various electronic circuits, BJTs are used either as an amplifier or as a switch. For a transistor, there are 3 regions of operation or 3 modes of operation: active region, saturation region, and cutoff region. A transistor must be biased in active region to operate as an amplifier. In saturation region, collector current of a transistor is maximum. So collector current is approximately equal to VCC divided by RC, and in cutoff region, collector current IC is equal to 0. So a transistor can be used as a switch if it is operated in saturation region and cutoff regions. For a transistor in saturation region, VCE is equal to 0.2 volt, and in cutoff region, VCE is equal to plus VCC. Now let us discuss the operation of a transistor as a switch. This is the diagram of a transistor used as a switch. So VB is connected to the base of the transistor through resistance RB. Supply voltage plus VCC is connected to the collector of transistor through resistance RC. Apply KVL to the base emitter loop. We will get VB is equal to IBRB plus VBE, or IBRB is equal to VB minus VBE, or IB is equal to VB minus VBE divided by RB, or RB is equal to VB minus VBE divided by IB. Similarly, apply KVL to the collector emitter loop. We will get VCC is equal to ICRC plus VCE. ICRC is equal to VCC minus VCE. That means IC is equal to VCC minus VCE divided by RC. Now let us consider a transistor in cutoff region. A transistor will be in cutoff region if its base current is equal to 0. So here the voltage VB is equal to 0. As voltage VB is equal to 0, there is no base current for the transistor. Base current IB is equal to 0. As base current IB is equal to 0, collector current IC is also equal to 0. As collector current IC is equal to 0, collector resistance voltage drop ICRC is equal to 0. As ICRC is equal to 0, VCE, voltage between transistors collector and emitter, is equal to plus VCC, as VCE is equal to VCC minus ICRC. So this is the equivalent diagram of a transistor in cutoff region. There is no current flow to the base. So base current IB is equal to 0. So there is no current flow through the collector. So collector current IC is equal to 0. So voltage difference between collector and emitter is equal to plus VCC, as voltage drop across collector resistance RC is equal to 0. Now let us consider a transistor in saturation region. A transistor is said to be in the saturation region if potential difference between transistor's collector and emitter is equal to 0.2 volt, or potential difference between transistor's collector and emitter can be approximated as 0. That means resistance between collector and emitter of the transistor is approximately equal to 0. It's almost equal to 0. So collector current IC is maximum, and it is given as IC is equal to VCC minus VCE divided by RC. As VCE is equal to 0.2 volt, we can approximate IC as IC is approximately equal to VCC divided by RC. And we know that collector current IC is equal to beta times base current. IB minimum is equal to IC divided by beta. So IB minimum is the minimum amount of base current to ensure that transistor is in saturation region. So IB must be greater than or equal to IC divided by beta. So base current of the transistor in this circuit must be greater than or equal to IC max divided by beta. When VB is greater than 0 volt, transistor's base emitter junction will be forward biased if VB is greater than 0.7 volt. So VB is equal to IBRB plus VBE. IBRB is equal to VB minus VBE, or RB is equal to VB minus VBE divided by IB, where IB must be greater than or equal to IC divided by beta. So now, let us design a circuit to turn on a bulb when output of an OR gate is high. So this is the circuit diagram. Output of the OR gate is connected to the base of transistor through resistance RB. So voltage drop across resistance RB is denoted as IBRB. And there is a relay connected at the collector of the transistor. So when transistor is in the saturation region, collector potential becomes 0.2 volt, or relay is energized. When relay is energized, that bulb will glow. So relay is energized if and only if output of the OR gate is logic 1. We can say relay is energized if and only if A or B is equal to 1. So in this circuit, we have to select a transistor, suitable relay, resistance RB, and an appropriate value of the voltage source VCC. Select the supply voltage VCC as plus 12 volt. Find the resistance of the relay coil using a multimeter. Let coil resistance is 200 ohms. So in this circuit, the collector resistance RC is equal to 200 ohms. Therefore, IC max is equal to VCC divided by RC. 12 divided by 200 ohms, 60 milliampere. Select a silicon transistor with IC max greater than IC and VC max greater than 2 VCC. Let Common emitter AC current gain of the transistor beta is 100. So minimum base current required to keep the transistor in saturation region is IB minimum is equal to IC max divided by beta, 60 milliampere divided by 100, that means 0.6 milliampere. Now apply KVL to the base emitter loop. We will get VB is equal to IBRB plus VBE. IBRB is equal to VB minus VBE, or we can write RB is equal to VB minus VBE divided by IB. So output voltage of an OR gate is plus 5 volt if the OR gate belongs to TTL family. VBE is equal to 0.7 volt as transistor selected is a silicon transistor. RB is equal to 5 minus 0.7 divided by 0.6 milliampere, that is equal to 7.16 kilo ohms. Select RB less than 7.16 kilo ohms to ensure that transistor is in saturation when output of the OR gate is high. Let RB is equal to 6.8 kilo ohms so that base current IB is greater than 0.6 milliampere. Any value of RB less than 7.16 kilo ohms will ensure that transistor is in saturation region when output of OR gate is high, as beta is 100. Selection of RB as 6.8 kilo ohms also ensures that transistor is in saturation region even if output voltage of the OR gate is slightly less than plus 5 volt. Much lower value of RB will ensure that transistor will be in saturation even if beta is less than 100. Finally, our circuit is VCC is equal to plus 12 volt, RB is equal to 4.7 kilo ohms. So when RB is equal to 4.7 kilo ohms, base current IB is equal to 0.9 milliampere. When output of OR gate is high, this also ensure that transistor is turned on even if beta is less than 100. When A is equal to logic 1 or B is equal to logic 1, base current is equal to 0.9 milliampere. So collector current is limited to 60 milliampere. Transistor is turned on. VCE is equal to 0.2 volt. Relay is in the energized condition. And when A is equal to 0 and B is equal to 0, output of the OR gate is equal to 0. So base current is equal to 0. So collector current is equal to 0. As collector current is equal to 0, relay will not be energized and the bulb will not be turned on. Thanks for watching Circuits Analytica. Enjoy learning. Please share, comment and subscribe our channel.